Chetan Arora. So he's from Department of Computer Science and Engineering, joint faculty at School of Artificial Intelligence at Indian Institute of Technology, IIT Delhi. Sir, welcome.
So good morning everyone. I hope you are having a nice time for this lecture. I was in the middle of the last lecture and I would really like that if we keep this session interactive. So please feel free. See, normally in the classroom setting I'm able to see the students' faces and that sort of tells me whether... Okay. So normally in the classroom setting I can see the student faces and then I know whether you are following or not, and then I can adjust my speed. So here, I think because of the lighting, I won't be able to see your faces. So which means that your questions will sort of be the feedback for me whether I should go faster or slower. Okay. So as it is, we have more slides than I can cover here. So the idea is that we'll just keep this, have some QA sessions in between, and I'll be able to know what you already know, and then we can skip some slides in between depending upon what your answers are. Okay, so let me just set up the context first before we reach to that place. So how many of you know what is the foundational model? Just hand raise. Have heard about that there is something called foundational model? Okay, so how many of you use ChatGPT? Okay, so everybody knows foundational model. Okay, so let me just set up the bigger context first. I mean, it sometimes helps to really take a step back and look at the bigger picture before we dive into the details. So this is how I would like to see how the things are really happening in last 20 years maybe, or 25 years. Okay, so I graduated in 99, so I have a chance to look at each of the steps here. Okay, so how many of you have done machine learning course? Almost everybody. So which can also mean that you know what is an SVM and what is a decision tree? Yes or no? No. Oh. Okay, so too bad. This is not going to be a course for machine learning, neither for SVM or decision tree. So we'll just assume that there is a black box called SVM, takes something, some sample data, and gives out some prediction. Okay, so that's an SVM. Can work with a small amount of data. I mean, when I say small, that's also relative quantity, let's say a few thousands. So now let's try to see what's happening in 2000 when we are working with decision trees and SVM. So this is what I call the homogenization of the algorithms. So I can give you an image classification problem, I can give you a sentiment classification problem, I can give you any kind of problem. And if you are in year 2000, what you know is SVM, I'll just apply an SVM. Okay, so unlike the regular software engineering where I give you a problem, you design a particular algorithm for it, you write a specific code for it, we are already seeing that I'm not writing a very specific solution for any problem. So you give me any problem, I'll just use SVM. So there is a single algorithm, SVM or decision tree, whatever you want to call it, which is running here. So single monolith, single homogenization, one algorithm, whatever problem. Now, this thing worked for about 10 years. Around 2012, we got AlexNet. So what we are seeing here is an homogenization of the algorithm. Now, come 2012, we have this deep learning, AlexNet. I hope many of you know AlexNet and CNNs. Hand raise. Okay, so we know AlexNet, we know CNNs. So one way to look at it is that this is a particular architecture. The other way of looking at it is that we are using the same architectures or the same features. Okay, so one way is that AlexNet is a particular layer architecture, 3-layer CNN, 2-layer max pooling, some fully connected in between. The other way to look at it is that this is all a transformation. Okay, so I give you a data, let's say an image, it passes through certain layer, comes a last layer, 2048 dimensional vector. So it's a transformation of an image to a 2048 vector. And this 2048 vector is a feature vector for that particular image. So I can call it architecture, I can call it feature. To me, they are now the. All right. So I can call it feature, I can call it architecture. But what we are seeing now in the LXNet era or in the deep learning era is that I'm only using few features. Okay, so LXNet is one kind of feature, ResNet is other kind of feature, VGGNet is other kind of feature. You give me a classification problem, I use VGGNet, fine tune this 2048, maybe learn this last layer. You give me a medical imaging problem, I take another ResNet, take another 1028 dimensional vector, put something else on top of it. So same feature vector, and I'm just doing something a little more on top of it to really make my problem work. So here I saw the homogenization of the algorithm. Here I'm seeing homogenization of the features. Same features, all problem. And now since about last 4 years, we are entering into a new era, which is a homogenization of the model itself. So I'm not going to use different features. I'm just going to use the same algorithm, same model for every problem that you will give me. Okay, so you give me classification, detection, NLP, whatever problem you will throw at me, I'll use the same foundation model. And if you think of it, this is not a new style of working. Okay, so now take Google search for example. Now, when I'm looking for a medical document, or when I'm looking for an educational document, or whether I'm looking for a tourist document, I use the same Google search, which means I'm using the same algorithm. What am I changing? How do I get different answers for different problems? Algorithm is same. What do I change? Okay, so somebody said queries. So you have different problems, same algorithm. What changes is the queries. So you make different queries, and based upon it, the algorithm is capable of giving you different solutions. And now think of the ChatGPT. Is it any different than, too much different than the Google search? You type in your query, it's the same algorithm which is running, and it gives you different answers every time. I can make that the ChatGPT is one kind of a model, and I can replace it with some other model, but this model also will be capable of working with different problems, the same model. And what will change is some input to the problem. In the case of the Google, it became query. In case of foundation model, I'll use a different word, which I call the prompt. So the model will remain the same, the prompt will change, and based upon what prompt the model will be given, the answer will be different, and answer is the answer to your problem, the solution to your problem. So that's how the foundation models are going to work. And what I'm going to do here is that for this foundational model, how I'm going to train this foundation model is that I'll just lay my hands on every data that I can use from the internet. It could be text, it could be images, structured data, speech, 3D signals, whatever data that I can give you, whatever data I can use from the internet, I'll just use and train this foundational model. And it's important because remember, when Google search algorithm is being written, it does not know what query you are going to make. So the model cannot be trained on a query because the query is not even known at that time. So the model has to be designed in such a manner that whatever query comes in, you should be able to handle it. In the same way, the foundation model have to be ready that I can be given any problem. This problem could be of image, this problem could be of audio, this problem could be of structured data. And once I have trained this particular model, I'm going to adapt it, the same model, okay? So now this is the same model which I'm going to adapt it to different versions of my problem, and I can convert that to a question answering, I can convert that into a sentiment analysis, etc. Now in this lecture, my primary goal is to tell you what I mean by this adaptation. Okay, because this adaptation cannot be a very sophisticated process. Okay, and it helps to also understand why it's a big deal. Now, can anybody comment on why the deep learning era sort of changed the thing? See, we had the machine learning, we had the CNNs all through. I mean, the first CNN was perhaps trained in 1990. In 2012 or 2014, something changed, and then we saw explosion of the applications in the machine learning or in the deep learning era. What caused it? What changed really? I mean, just raise your hand, I'll ask somebody, and then that person has to shout. Okay.
Availability of data.
Availability of data. No, why did the applicability change? I mean, availability of data is an important concern, but why suddenly I am seeing so many applications? No. So these are tools to develop the solution. But why do I suddenly feel that I can make solution? Why was I not able to do 2010? I mean, availability of data, for example, the medical imaging is thousands of pictures. That was available in 2010 also. See, we have to really understand how a traditional programming is done and how a current modern deep learning is being done. See, I'm sure that all of you are, or most of you are computer science students, you know sorting. So once you know the sorting, what happens really? I mean, when I say that I'm writing a sorting algorithm, what is happening? For the computer, I give you an unsorted array, you write a program. And these two things, the unsorted array and your program, goes into a computer does something and comes out a sorted array. That's how the traditional programming, when you write the software, that's how you do it. What happens in a machine learning or in a deep learning? I am giving you an unsorted array. I'm also giving you a sorted array. That's your output that I need. I give it to an optimizer, which is also a computer program, and comes out a neural network model. What is a neural network model? Some sequence of multiplications and additions. So it's also a program. It's just that this program is not written by a human being, but it's a program. So in the classical programming, classical software engineering, I gave you the input data. Somebody wrote a program, I gave it to a computer, and then the output came in. In the machine learning, in the deep learning, I gave you an image, I gave you its classification label, what is the output that I want, and the computer generated a program. Now, why this slight change in this whole should be a big deal? Because this program was where most of the expertise was needed. See, if I'm doing a cancer detection, I need to be a radiologist to really write that program to do cancer detection. So this writing a program is where most of the expertise is needed. And the moment I flip the game and I say that this expertise is not needed, then a computer programmer like me can guide a computer to generate a program which will work better than the radiologist. And now suddenly there's an explosion of the applications because I did not have those many expertise that were really required. And after 2014, this expertise is not even needed. Give me input, give me output, I'll generate the program without necessarily being an expert in that domain. And now the space of the application that you can do suddenly explodes. Now, how does it change in the foundation model? This discussion started because I wanted to say why the foundation model is a big deal. Now, what we understand is that the AI talent is also less. So the people who can take input and output and ask a computer to generate a program are also very few. What if I say that that expertise is also not needed? So the tomorrow's program will be like a Google search. So your parents, your friends non-tech, non-computer science, will be able to prompt the chat GPT and generate the program. I think you guys are also doing it. So you use Copilot. Prompt the Copilot and comes out the program. So you don't need to really know what to do. So I'm going to decrease the requirement of expertise even one more notch. And the hope is that the domain, the user space of it is going to further explode more than what we saw in the deep learning. And that's what we see. See, I see my kid, class 10, 10-year-old child, 15-year-old child also using ChatGPT to write programs. So I don't need the computer programmers, computer scientists, computer science students to really write the program anymore, even whatever program we were writing in the deep learning. And that's the big deal. Because the space, the user space who are going to use these AI will become almost everybody. Because the interaction will happen through the natural language, either typing or audio, and programs will keep getting generated. Okay, so that's what we are going to do. So I'll adapt it, and this adaptation process has to be very, very simple. That's the big deal. So this adaptation process cannot be sophisticated, cannot require too much expertise. And that's what we will see in the second half of the lecture, how that happens. And I should be able to adapt it to any application that I think. So something that will be common. See, if I'm going to use all kinds of data, I cannot have all kinds of label for that data. So either I can say that I will use small amount of data and the labels with it, or I can say I'll use large amount of data with no labels onto it. That's my trade-off. And what I'm choosing is that I'll use large amount of data without labels. So I'll use all kinds of data that you will give me. I'll not ask you the labels. And what I'll instead use is the self-supervised, which I hope in the previous lecture you have already understood how to do this self-supervised. So I'll give you an image, you do some transformation, try to bring it nearer, do contrastive loss, etc., 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 but you train your model. So all these foundation models, or most of these foundation models, will be trained in a self-supervised fashion because that's the only way we know as of today to really use all this data without labels. The second stage, which I'm going to change, or which I'm going to describe now, so that was a pre-training stage. So I took a model, large model, used all kinds of data, but it's an ML model. It's a neural network at the end of the day. It's not changing. So I took a large neural network, did all kinds of training, pre-training we'll call it. So I did all kinds of pre-training on the data in a self-supervised fashion and came a model. Now this model is not supposed to do any specific task because you have not even told it the task yet. So then this model have to be fine-tuned in such a manner. Now I'm using this fine-tuned word in a little more generic, in an English sense rather than the machine learning sense. I'm going to fine-tune this model. I can also use the word adopt here. I'm going to fine-tune this model so that it becomes usable for a certain task that I want to do. So this part you have already seen, and this part is what I'm going to describe. So I'll give you a model. It's a 130 billion model, parameter model, or 1 trillion parameter model, doesn't matter, something that you can load in your memory. And you have to adapt it, fine-tune it for the specific task that you want to do. And this fine-tuning adaptation, whatever word I use here, cannot be too sophisticated because I want to increase the applicability. It has to be very, very simple. And that's what we'll see how to do it. So the word that I'm going to use for it is what I'll call the PEFT. The PEFT stands for parameter efficient fine-tuning. So I'm still fine-tuning the model, but it's going to be parameter efficient. I'm not going to introduce too many parameters here, and I'd like to quickly adopt using few samples. And when I say few samples, the samples could be 8, 16, 32 of that order. So you have a particular model, and I give you, okay, you have 10 examples input output. Can you really update your model with that? Okay, so that's the target. Now before I can go into PEFT, I have to use certain words there. Okay, so I would like to be sure that we know those words. So when I say the prompt or when I say the query, and I say I'm inputting it to a model, I need to really make sure that you understand where I'm inputting. See, because ultimately it's a neural network, it's a vector. So I'm inputting a certain vector to a certain neural network. Where am I inputting? So that part should be known, which means that I need to take a little step back and tell you what the basic architecture is. So in that basic architecture, you will know, okay, there are certain vectors that are inputted in general. And when I'll do the PEFT, then I'll say which vectors are going to change or which vectors are going to be trained for. Okay, so the basic architecture that we are using in most of the foundational model are transformers. Now again, in hand raise, how many of you know what is a transformer? Okay, so almost everybody knows. So Q, K, and V, if I just use the word, you know them. Where are they? Query, key, and value. I mean, again, I have to make a hand raise because I'm not able to see your face expressions. So how many of you would know where is Q, where is K, where is V? Okay, I'm seeing few hand raised. So I'll just go quickly over it, but please feel free to just ask few questions, which will tell me that I need to go slow, if at all. Otherwise, I'll just go at a same speed. So before I can just tell what is a transformer, it's important to know why did the transformer even came into the picture. So I'm happy, or I was happy with the CNN, the convolutional neural network, which actually started this whole deep learning thing. Now, why am I really so concerned that I should be using something else? Now, so the CNN actually works with two main criteria or constraints. So one is that they are locally connected kernels. So I take a particular weight vector, a particular weight window, let's say 3 by 3 window. These are 9 parameters, or actually 9 times the number of channels. Okay, so I give an answer. So let me just ask a question. So let's say I have a convolutional neural network which takes an RGB image as an input. Okay, so for the sake of grounding, I mean, just keep on noting the numbers that I'm saying on your papers. So I have a CNN. The input to that CNN is 224 by 224 RGB image. I have a first layer, which is a 3x3 convolutional layer. Okay, how many learnable parameters in this layer? I mean, raise your hand and then I'll ask somebody to answer. Yeah. So 224 by a convolutional neural network, 224 by 224 by 3 RGB. I mean, 224 by 224 RGB image, which means 224 by 224 by 3 tensor. And I have a 3x3 convolutional layer. How many learnable parameters? So raise your hand and then I'll ask. Okay. Yeah. So 224 by a convolutional neural network, 224 by 224 by 3 RGB. I mean 224 by 224 RGB image, which means 224 by 224 by 3 tensor. And I have a 3x3 convolutional layer. How many learnable parameters? So raise your hand and then I'll ask. Okay.
Do we have bias or not?
Add
Bias also?
Yeah, go on.
From 3 channels to channels.
So it's a 224 by 224 by 3 tensor, because I've already said it's an RGB image.
Yes.
And it's a convolutional layer 3x3. How many learnable parameters?
What is the number of output channels?
Okay, so so let's say 54. That's it. The next step.
It will be 54 times 3 times 3 times 3.
Okay.
Plus 1 is bias.
All right. Thank you. Good. That's the right answer. Now let me just make the problem complicated a little bit more. And if you had remembered it now, I just want to delete that advantage. Now let's say I give you a video. Okay. Now it's a video clip. So instead of one RGB image of 224, I'm giving you a 16 sized clip. So 16 RGB frames, 224 by 224 by 3. Same convolutional layer on this clip now, and same convolutional 3 cross 3 cross 3.
Same number of parameters.
How many parameters?
3 by 3 by 3 by number of 54.
No. So then there is no difference in image as an input and video as an input in the same number of learnable parameters? Somebody else? Okay, so there will be one more tree. So it's a 3 cross 3 cross 3, which is a kernel size itself now because it's a video. And one more tree because it's operating on an RGB image. So in the CNN, the previous question that I asked, it was an input image which is a 2D. So 3 cross 3. It was operating on a vector data, and the size of the vector is 3 because it's an RGB image. So it was 3 cross 3 cross 3. In a 3D, like in a video, my kernel itself is 3 cross 3 cross 3. It's a 3D kernel now. But it is still operating on a vector data because it's an RGB image. So the number of learnable parameters will be 3 cross 3 cross 3 cross 3, 4 threes. And then plus 1 if you want to add the bias also. Okay, now let me just change a problem question a little bit further. Now let's say instead of an RGB image, I give you a satellite image. Okay, satellite images are typically hyperspectral images, and just like you saw in the RGB, they typically have hundreds of channels. So let's say I take an hyperspectral image which is 100 channel image, and I give it as an input to a neural network, convolutional neural network. First layer, 3 cross 3 convolution. How many parameters now? So I'm training a convolutional neural network which takes an hyperspectral image as the input. Hyperspectral image has 100 channels, and rest of the details remain the same which I asked earlier. So it's a 3 cross 3 convolutional layer that I'm putting, and 54 output channels. How many parameters now? Okay, so because we are short on time, so I'll not wait for the answer now. So it's a 3 cross 3 window. It's a 2D convolution which is running. It's a 2D convolutional running on a vector data, which was earlier 3-dimensional because it was an RGB image, and now it became a 100-dimensional because it's a hyperspectral image. So the number of parameters now will become 3 cross 3 cross 100 because my vector size is 100. Plus 1 if you want to add bias, and multiplied by 54 because these are the number of output channels. Okay, so we understand that now. Now, what is key here is that whenever I computed the number of parameters, you never ask me what is the image size, like 224 by 224, because that does not matter. It's the same kernel or a window which I'm just sliding over the image. Okay, so this is how I'm trying to show it here. So this is a window which sort of does a weighted sum and then it gets an output. So I can run it on arbitrary sized images because it will simply scale my output also to that size, does not change the parameter, does not change anything else. So what is important takeaway from here is that the features that I'm learning, so these are my features. Okay, so these are my features which I'm trying to learn or trying to predict or trying to compute from my input data. And these features depend upon this 3x3 window, because that's what I did the weighted sum for. Okay, so it's a locally connected network, which means these are local features. The other thing that happens as a consequence of how I'm learning my network is that these weights are shared. I do a weighted sum at the top left of the image. I do a same weighted sum in the bottom right of the image. Which means that if there is a particular feature, let's say there is a vertical edge here, this feature will become high, the output will become high. If it is a vertical edge here, this feature will become high, let's say. So the same feature, irrespective of its location, will excite my output, will activate my output at a different location. Okay, again, that's a consequence of how am I training. And that's useful because let's say if I'm trying to classify dogs, you may have shown me the dog on the top left, but I sort of automatically know how the dogs will look like on the bottom right. You don't have to give me every sample to really train my model. So it's inherently translational invariant. You show me an object or feature on one side of the image, the other side is automatically learned. So that majorly reduces my training data requirement. Now, these are the two things which will define my CNN. Now, let's try to see the consequence of it, how the feature is. So let's say I'm trying to classify it's a matchstick. Okay, so given a particular image, I have to say whether there's a matchstick in it or not. That's my problem. And I train a neural network for it. Now, what you know is that the neural network will learn 3x3 features, let's say, or maybe I do 11 by 11, so 11 by 11 features. So there is some local feature that I can learn. And then when I do the second and third and fourth layer, these features will start composing themselves. So I say if this feature is present, that feature is present, so I sort of compose them. And these are translation invariant features. So let's hypothesize that maybe these are the features that a neural network will be able to learn. That if I see a flame, if I see a stick, and these two occur together, then it's a matchstick. Okay, because it's unlikely that the model will be able to learn the whole thing. I'm just using small features. So I'll be using small features and the composition of them. That's how the neural networks are behaving in a layer-wise fashion. So if this flame is present, if this stick is present, matchstick. If this flame is present, this stick is present, matchstick. So I learned two features, flame and matchstick, and I learned to compose them. If these two are present, it's like an and, then I'll say it's a matchstick. So this is what I have learned. Now, is this a matchstick? For a neural network, it should be. Because I see lots of flames and I see lots of sticks. Every feature that I learned, every composition that I learned, it just fits in. But we understand that it's not a matchstick. And if you try to analyze how a neural network is learning, I mean, so somebody did this visualization class-wise. So this is what a neural network dumbbell is. So how we do it is that I start with a black image, predict it's a dumbbell, and then I backpropagate so that I want to increase the confidence of the dumbbell from the black image. So I change the image, and I change the image, and I change the image until the dumbbell becomes 1. Now, if I see how did I change my black image? So this is what the black image has changed to. So this is what a perfect dumbbell looks like for the neural network. Now, I'm not sure whether you are able to see some faint images of the dumbbell. Similarly for the cup. So you should be able to see, I mean, these slides will be available to you. I don't know whether from the end you can really make that out. So there's a faint image of cup here, there's a faint image of cup here and here. Okay, so the lemon, so there are all lemons here. Dalmatian is really a checkerboard for a neural network. So I trained the model for learning specific features, and it learned exactly that. So what I'm trying to impress upon is that the fact that I automated the process of giving input and output and asking the model to learn itself is not unconstrained. the fact that I used CNN, I have already constrained the feature in a certain manner. That I will use local feature, I'll use translation invariance. Now, whatever features will be learned will be modulo these constraints. Okay? Now, these will have its own implication, as I said, that I can backfire on the matchstick if the composition is going wrong. And there is a scope for changing this constraint. So I'll keep the neural network the same. I'm still using the neurons, I'll be still using the neurons, but I will not pose these constraints of local connectedness and translation invariance. I'll say, let's try to train it in some other manner. And that's where the attention comes in. So just like I was biasing my neural network in a certain way in a CNN, now I'll bias in a certain other manner. Now what is this certain other manner? I'll use the word attention here, and this is again like in English attention. So if as a human being I ask you, okay, tell me whether this image contains a flower or not. How do you do? You scan the image, look for the certain parts, you attend to those important parts, and then try to make up your mind whether this attended part is a flower or not. And then based upon it, you'll give your decision whether this is not. So I'll try to mimic the same process. I'll say I'll attend to different parts of my input, and then whatever the features are from that part of the input, I'll attend as in the multiplication. So because what you're seeing is that if it's not an important part, you're not even trying to ask whether it's a flower or not. And if you say the flower, you multiply it with the attended part. So there are some parts which you are not attending which are 0, there are some parts which you are attending which are 1. And then you take the feature, multiply them together, and then you say whether there is a flower or not. So I'll just mimic the same process in a neural network style. Okay, and I'll use the same abstraction that I have a neural network here. I have some neurons which I can combine it in any manner. So this is what I'm going to do now. So it will help to really change the analogy at this moment from the neural network to a database. Now, let's say if I give you a database, which is really a table with many rows, and I ask you how many students here got the score above 50%. Okay, now what will you do? You will check a row. So first of all, I'll give you a query which is 50 here, or greater than 50 here. You will check against each row. You will say that whether this row the student has more than 50 or not. Give 1 if yes, give 0 if not. And you do it for every row, and then you add across all of them. Okay, so first you assign the weights to each row, and then you do a weighted sum of row versus plus the row and the weight that I computed. So the same analogy that we are now giving in the input vector. So I'll have a query vector Q. So which will be of size NQ, which will have the number NQ. So I'll have NQ query vectors, each of size DQ. Okay, just like students greater than 50 marks. There will be input vector, these are like the rows of the table. So I'll have this X, this is like one row. It will have NX the size, the vector, is like the number of columns. And the DQ, okay, so I should have used just D here, some DX here. Then there will be some part or some transformation of the input which I will use to compare. So for example, right now I said that student with greater than 50 marks. So you have to compare marks with the query. I could have said the students which are greater than 50 marks and of age 18. So there's a X which is the full row, and I make a transformation to it which is greater than 50 marks and age 18. So let's call this transformation as the key. So I made some transformation into the input, and I'm calling the key that. So I'll have those key vectors, and once I have found out these keys, I'm going to find out how much the Q and the K, Q vector and the K vector are similar. So are they greater than 50 and age 18, or are they, I mean, depending on my query. So I have already converted this key from every row. I'll do this Q and W, some kind of a weight computation based upon that, or attention computation. Once I have computed the attention, then I'm going to use my input row, multiply with this weight vector, this attention vector, whatever I had, and then I'll find out whether I want to add it into my output or not. So that's my output, which is W. Okay, now let's try to see here. So I have my Q vectors here. So it's like how many students with query greater than 50, how many students with age 18. So I can ask different queries. I have my X's here, which are like the rows of my table. So first thing that I'm going to do is I'll convert them into a keys which I can compare with the Qs. Okay, it's like greater than 18, greater than marks greater than 50, like that. Once I have done that, I'm going to compute the alignment between them. Whether this key does have marks greater than 18 or not. Whether this key does have marks greater than 18 or not. So the different queries, sorry, this one. So this is greater than 18 age. So whether the first row has greater than 18 or not, whether the second row has greater than 18 or not, whether the third row has greater than 18 or not. The second query represents some other query, marks greater than 50. So whether the first row has greater than 50 or not, whether the second row has greater than 50 or not. Okay, so that way. So this is the alignment between my query, whatever query I asked, and whatever key I generated from that particular row. Once I do that, depending upon this query and k vector, this alignment can come out to be some arbitrary numbers. So the next thing that I would like to do is I will do some kind of a normalization. Now the typical normalization that I'm going to use in this context is the softmax, which means that all these elements, because they were representing my query result for the Q1, all these vectors should sum to 1 and should be non-negative. So I can say that, okay, this matches the most, this does not match, this does not. So now, right now it's like searching one element out of the whole table. Okay, just that I'm not saying 1, 0, 0. I can say 0.7, 0.3 and 0.1, like that. So that as long as they sum to 1. So I'll give different weights so that they are all non-negative and sum to 1, and this is what I'm calling attention. And remember, it's a softmax over the way I have shown it over the columns. Okay, so this is one mistake that I've seen students making often. What is a softmax for a matrix? Nothing. The softmax is over the columns. Different people, different authors can represent the matrix in different ways. So let's not even hard code the columns. Let's say the answers for the same query across different keys. So it's the same query across different keys. That's what I'm softmaxing, because I need to really know which row matches the most to my query. So once I have done that, I'll generate another vector from this v, another vector from this x, and I'll call it the value v. And essentially what I'm going to do is that whatever weights I have computed here, I'm going to multiply and add. Okay, so in my case, now these are my queues, the queries which I posed to my model. These are my keys, which are my keys, which I'm matching them again, which I'm using to match. And these are my values, which I'm doing the weighted sum with the attention that I have computed. And what is the attention? It's basically the similarity between the Q and K after doing the softmax. Okay, these are the two operations. Now the similarity between the Q and K in the transformers will be computed through a dot product. So I'll just take a dot product. Dot product is a good way to measure the distance between the two vectors. So that's what I'm going to use. So if the Q is very similar in the dot product, similar in the direction, which will have the high dot product, then it will get the higher number in the probability vector. That's what I'm going to do. Now there are two different versions of it. How am I going to do it? So one is called the self-attention, in which I do not get any other input. So it's like the different parts of my input attending to each other. And now this is important. So for example, let's say I give you an image and I ask you a question. I give you an image in which there is a yellow circle in the middle of the image. Of course, there are some other things also along with it. Now, what does this yellow circle represent? And your options are a lemon or a ball. How will you answer that? Now, what you should realize is that if I just tell you this information, there is nothing to really disambiguate whether it's a lemon or a ball. Both can be yellow circles. The disambiguation can only happen if I tell you what is the context. If I show you a kitchen table and a knife and a gas somewhere, you say it's a lemon. It's unlikely to be a ball. If I show you a green field and some people standing over there, maybe it's a yellow is a ball. So what feature I should describe of this yellow circle really depends upon what are the other features. What is the other context? And that's what we are trying to say. So imagine that this x1 is that yellow circle, some part of the input, and this x2 is the green field or the kitchen, depending upon what the other context of the image. And what I really want is that this x1 should really look at what is x2 and x3 before trying to say what am I. And that's what I'm trying to mimic. So what I'll do, I'll convert this x to the q's, some transformation that I learn. I'll convert this x to the keys also, and then I will match against them. So you can imagine that what I'm trying to say is that whether this x1 is a kitchen, whether this x2 is a kitchen, whether this x3 is a kitchen. That's what I'm trying to learn. Okay? So whether this is a kitchen or not, I am putting this into Q, etc. and similar into the K. And then what I'm really deciding is whether this is also a kitchen and this is also a kitchen. Okay? Or whether this is also a sports field and that is also a sports field. That's Q2 maybe. Once I have learned that, so I understand that this A11 will now represent, not A11, let's say, let's say A12. Now this A12 represents whether the Q1 aligns with K2. And what does it mean? Let's say the Q1 is the lemon or the yellow ball and Q2 is a kitchen table. And now what you're saying is, are they really same or not? Should I really attend to this portion or not? Once I have attended, I'll determine yes, they are same, so this should be high, which means that the V2 feature should be of a lemon and not of a ball. Try to generate in the output. So I'm really doing the weighted sum. So I first take this x1, learn this weighted sum, and then use this weighted sum to really get my output y1. But remember now this y1 output has really seen the features of the other parts of the image. And then I said y1. So this y1 should have disambiguated by now whether you want to say a ball or a lemon. Okay, so that's where the attention is going to play the role. There is, so when I use the Q's separately, so if I'm giving two inputs to my model, a Q and an X, that is called a cross attention because it's like one input is Q, other input is X, and they are cross attending, they are attending to each other. And when I take a single X and I generate the Q and K's both from the same X, I'll call it self attention because the input is attending to itself. So now it's a self attention and a cross attention. So remember, because in next few slides I'm going to say that I take this prompt and put that into a Q vector. So then you should be able to relate back that where the Q vector is, or what will really happen between the prompt and the K, or prompt and the input. Okay, so these are the words which you should now memorize. There is a Q, there is a K, there is an X. The X generates Q, then it's a self-attention. If Q comes separately, slightly differently, then the K and the Q are separate vectors, and then it really checks the alignment between the two sets of input, which is Q and K now. And based upon it, I generate a feature map of the X. Now, what can also happen, just like we were using the number of outputs in the CNN. So I learn a kernel, but I can learn 100 kernels. In the same manner, I'm doing the attention, but I can do the attention multiple times. So how will I do that in the case of the attention? Is that I'll take this vector X and I'll divide, let's say, it into 3 parts. It's like, let's say I have a 30-dimensional vector. So instead of saying 30-dimensional vector, I say, I have 3 10-dimensional vectors. Now for each of this 10-dimensional vector, okay, so now this is 10-dimensional, 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 I've just split it into 3. I'll do the same attention that I described you, but for each of these subsets separately. So one set is x11, x12, and x13, 10-dimensional. The other set is x21, x22, and x23, and similarly the third one. Now, all the self-attention, cross-attention will happen in the same manner, and I'll get individual Ys, which I will concatenate back. Okay, so it's important to first know what is going into the input and output, and once you have understood what is going on, then quickly abstract out. So all that is happening, just like in the CNN, some input goes, some output comes. It's like a tensor input and tensor output. You understand what goes in input, but because you have to abstract out very quickly, you say, okay, some transformation happens. In the same manner, there was an X which was an input, some transformation happened and I got Y. Which means I can potentially repeat this block later on, because this Y will become X for somebody else. So it's a transformation, but this transformation happens slightly differently than the CNN now. The CNN was doing local connection and translation invariant. There is no such thing here. I attend to different parts of my input, do a weighted sum, and then do a weighted sum. Yeah, that's all. So the kind of features that I'm learning are different, but I'm learning features. And nothing that I'm doing is something that cannot be differentiated. And that's also important, because ultimately I'm going to use the same backpropagation algorithm which I use in the CNN for this purpose also. It's just that the gradient computation is now slightly different than what it was in the CNN. Okay, it's the same softmax, it's the same weighted sum. It's just that in the CNN the weights were learned, and whenever you were doing it for the input, it was the same set of weighted sum that you were doing. In the case of attention, you are computing different weights every time. Okay, but notice that I use the word that you are computing different weights every time for every input. You're not learning different weights. So I just did dot product between Q and K to learn the weight. So where are the learnable parameters here? So where are the learnable parameters in this attention block? Hand raise and louder. Yeah. Okay, so I understood something, but I'm not sure whether everybody else understood. So the weights are in these arrows. So I converted this X, transformed this X to a vector Q. I transformed this X to K, and I transformed this X to V. And this transformation is a layer, is an MLP. If it is a single layer MLP, it's just a transformation matrix. Okay, so one layer of the neural network is the linear transformation. So the weights are not here, the weights are not here. The weights are here. So I learn 3 sets of matrices, 3 sets of weight, one for x to q, one for x to k, one for x to v. Right? So, as I said, so I can have a transformation, but I can have a different set of transformations for the different set of inputs here, which will act like the convolutional channels. So this will learn different attention on the part, this will learn different attention on part, this will learn different attention on part. So somebody say that I want to look at the kitchen, somebody will say I want to look at the playground, somebody will say I want to look at the forest. So different attentions will learn, so different matrices will learn different kinds of attention. So this is what we will call multi-head self-attention. Okay, so there are different heads that I have now. So now, just like we do in the CNN, so we first learn the convolutional layer and then we say how do I stack them into the CNN. In the same manner, now we have understood what is an attention layer, I have to make a neural network out of it. So what do I do? Now I'll just use that attention as a block. So I will give you an input x. So these are input vectors, x1, x2, x3, etc. I'll do self-attention. Okay, so now I've used the word self-attention, but you have to really imagine this block when I say self-attention. So something will go here, something will become q, something will become k, some dot product will happen, the weighted sum will happen and come the y. Okay, so this whole thing is this block now, which is self-attention. I'll do a residual connection. Okay, so input will directly go to the output at addition. This is just like the resonate that you have seen. I'll do a layer normalization. So now this is also a new word, the people who are coming from the CNN. So in the CNNs, we use batch norm typically. So the batch norm is when you take all the pixels and do a norm over the batch size. Okay, but the parameters are computed differently for different channels. In the case of the layer norm, I'm doing it for a single sample, no role of the batch here, but doing for the all channels together. Okay, so the normalization strategy is slightly different. It helps more in the attention. But I get a vector. Now I get a vector and I do an MLP. Now this is also important because this MLP acts independently on each input vector. So I take this x, the self-attention will generate some y for me, and this y will pass through an MLP and will get me an output. Okay, so how many x is here does not matter at all. So just like in the case of the CNN, the size of the image does not matter. I learn the same parameter and I just use the same. In the case of the transformer, the number of these x's does not matter, because I'm transforming each input separately, I'm applying each MLP separately. So how many vectors I have does not matter. I mean, of course it matters in terms of the memory that I will use, but I can train it with the 10 x's here and I can test with the 20. That's not a problem. Just like in the case of the CNN, I can train with a 224 and I can test with 448. Okay? And then I'll have another connection, residual. I'll do one more layer normalization and then get me y. Okay? And now this whole block of self-attention layer, MLP layer normalization is something that I'll call a transformer block. So this whole gray region now is a transformer block, or just like in the case of convolutional layer, it's like a one layer for you. This layer is not learning convolutional features. This layer is learning attention-based features. But now you know that when I say x, now this number of tokens can change without really bothering you. And this x are going to go into the q and into the k, and some similarity will be seen. Okay? So So the typical transformer, which was, for example, presented in Vaswani's paper, had 12 such blocks. So it's like one block, other block, other block. The size of the query vector, that's important because the matrix will be determined by that. And whatever the size of the Q has to be the size of the K also, otherwise you cannot do a dot product. So the size of the Q was 512 in their case. And when I said multi-head attention, so they were using 6 heads in their architecture, just like an LXNet. So just like you see the LXNet, now it's the paper, this Vaswani's paper, and this is the architecture that I'm describing. 12 blocks, 512 dimension Q, 6 heads. Okay. Now this transformer block will be pre-trained with lots and lots of data, something that you learned in the last lecture. For a different, for example, if it were an NLP, each of this x1 will become the words. So I give you a sentence. So x1 is one word, x2 is other word, x3 is other word, x4 is other words. And then what you do is you self-attend, which means one word attend to the other word and try to learn a feature representation of itself. Once I have learned a feature representation of these individual words, which actually form a sentence, I'm ready to do something on top of it, which could be emotion classification, which could be next word prediction, which could be something else. But the important thing is I've learned some feature. So from this X input to this Y output, I could have used CNN layers or I could have used attention layers. The same way for the images also. So if I were having an image classification problem, so what I'm going to do is I'm going to split this image into the small patches. These small patches will become the words for me now. So just like I had this x1, x2, x3, now these are the patches which are, so just like I was giving an example, this could be a yellow patch for which I would like to decide whether it's a ball or a lemon. So these are my patches now. And these are x1, x2s. I convert them into vectors, d-dimensional vectors. So there is something that which I did not tell you, which is positional embedding. So I need to really add something into it. And then I'll apply this transformer block. Okay, and as I said, transformer block is attention, layer normalization, MLP, all this stacked together. So what you should remember as an input-output rule, whatever the number of input tokens, so this is now I'll call the tokens, so x1, x2. Because this is my image, I converted it into patches, so each patch is a token. In the case of sentence, each word could be a token, or typically even the subset of the word is a token. So it's slightly more detailed than that, but for the purpose of this discussion, you can say each word is a token. So I have a token here which corresponds to a vector. So whatever the number of input tokens is the number of output tokens. All the MLPs, etc., run on each token separately, which means the number of tokens does not matter. So I can have different input image size than the trained one, and that should be completely okay. But the dimension of the input matters. So if I have trained for a 512 dimension, I have to stick to 512 dimension because all my transformation matrices are trained in that particular way. Okay, so if I decide to add something here, then the whole thing changes because the whole transformation matrix will need to be learned afresh. Okay? And then this is the output vector, and you can keep on repeating that. If I have to do a classification, what I can do is I can add an extra token here. Now remember, in the attention, in the transform block, the number of tokens does not matter. So there were 16 tokens here, so I add a 17th token here. Now what's the purpose? Now this 17th output vector will be a weighted sum of all the V's from here. So it's like that I have taken an image, I have learned feature representation for each patch, and then I do this addition of all these feature vectors, the weighted sum of course, and then decide what this image is. So it's an image classification. So what I have to do is, I have to just in the last layer or last couple of layers, add an extra token here. And whatever is the output of this vector, eventually I'm going to learn one more MLP on top of it and do the classification. So the gradient will flow like this now. So all these output vectors are redundant. They are not useful for me. They were just learning the representation. What I'm really saying is that at the last layer, this token has actually learned the aggregated representation of the whole image. And in the transformer language, sometimes this will be called the CLS token or the classification token, because the purpose of that is to do the classification. Okay, so when I'm doing a representation learning, I can just say that these are some input embeddings and these are some output embeddings, and I can pre-train in the manner the Binod was telling you earlier. Or for the transformation, there are other kinds of pre-training that I could have done, which is called the masking, for example. So I take this, let's say sentences, I hide one word into it, and I say that the output should be able to generate that word, hidden word or the masked word. So this is called an MAE training, masked autoencoding, because I'm trying to encode myself just like the autoencoders, but with the masking. This is a very easy self-supervised task, because you just take a sentence, hide one word into it, and ask your transformer model to learn what was the hidden word. So it has to learn the whole context. In this context, what word can come, etc. And in turn, learn the representation. At each iteration, you mask different words, or you can mask more than one word also in one iteration. So this is the BERT style of training. The OpenAI style of the GPT style of training is the next word prediction. So you take the word and you predict the next word. You take a sentence and predict the answer. Answer is also next word in some sense. Okay, again, you can do a lot of pre-training with that, because the internet is full of sequence of sentences. So take one sentence, say what should be the next word, and that's all. And you train your transformer model with that, and that's it. So ultimately, the agenda is that you want to train the weights of this transformer, which essentially means that you want to learn the transformation matrices which were converting X to Q, X to K, and X to V. But these matrices itself are huge, because the dimension that I'm talking about, so right now I said 512, but in GPT I may not have the immediate number, but I think I may have the table later on. This dimension will go to 10,000. So now you can imagine that for an attention, the DQ matrix, so you are learning a transformation matrix which takes an input which is 10,000 dimension and converting that to, let's say, a 4,000 dimension vector, which is Q. So the dimension of the matrix is 10,000 cross 4,000 in one block. And I'll have many such blocks. Okay, so this is the background. Now let's move to the prompt tuning, or the PEFT. Now let's say, so we now know what is the transformer. So when I use the word Q and K, you should be able to relate to that, what I'm trying to say. Now how do I use it? So I gave you a full transformer architecture. So this transformer architecture is nothing but the repetitions of this transformer block that I said. And transformer block is nothing but the multi-head attention followed by some layer normalization and MLPs. Okay, so this is the whole big architecture that I give. The building block is very simple, just like in a brick. So the brick is attention and one transformer block. And let's say I decide to fine tune. Okay, now fine tune in the style that you know. Take the model, give me input and output, back propagate and update the weights. So what am I looking at? So these are some of the statistics. I think this is what I was referring to. So different GPT-3s. I mean, this was the paper that got published in 2020. So after that, OpenAI became closed AI. So we don't have the numbers there after. So GPT-3 we know what is there. So the GPT-3 different models. So the large one that you have is 175 billion. The number of layers, okay, so something that I said 6, I think in the Vaswani, has become 96 now. Okay, the dimension of the model, which I was saying, 512, have become 12,000 now. The number of heads that I was saying 6 or 8 there have become 96 now. Okay, and in any case, this multiplied by this should be this. Okay, so it's like that I'm dividing 12,000 dimension vector into 96 heads, and the dimension of each head has to be 128. It's like splitting the vector. The batch size that we are talking about is 3.2 million. Now, I don't know the batch size. So Binod was explaining you the SimCLR in the previous lecture. So what he was saying is that you have this batch, you take some anchors, you say have some positive sample, you bring the anchor and positive closer and anchor and negative farther. What is the batch size in the SimCLR? 4096. Okay, what were the batch sizes you use for the CNNs typically? 32, 64, 128, like that. Why does a SimCLR requires 4000 batch size? Why would 64 or 128 not work? So remember that, let's say all you're doing is that I give you 10 points and I say that, okay, push them farther from each other. So I give you cat and cat. So one cat image, other transformed version of the cat, I say bring it closer in the transformation space. I give you a dog, a horse, one more elephant, etc. Bring this representation farther from horse and elephants. That's all I'm saying, right? So that's what the contrastive loss is doing. It's learning, updating the weights in such a manner that the cat representation goes away from the horse and dogs and comes closer to the cat. And the question that was asked at that time was, will it overfit into the cat? And I think the problem is actually elsewhere. The problem is not really overfitting cat to cat. I think I can survive that. The problem is, what is the representation of a background? And when I say background, what is not cat? Okay, so see, I do this video analysis for a long time. So I was said in 99 when we were doing this background subtraction, is that it's very easy to model the representation of a foreground. It's very difficult to model the representation of a background. So I can very easily tell you what is the representation of a car. It's very difficult for me to say what is not car, because now it's universe. So my problem is not really bringing cat and cat together. My problem is how to bring cat away from everybody else. So while I bring the cat away from the horse, am I making it closer to the zebra? So you have to give me as large a possible as this universe, so that I can really, while I'm going away from somebody else, I should not become closer to somebody else which I don't want to be. So the large batch size is really important for the self-supervised learning, because there's no anchor otherwise. I mean, I'm just pushing the representation away from something else. But when I push something away, which is that I'm getting closer to, is what the problem really is. So the 68 dimension means that I can give you 68 samples of the universe. 4000 sample means I can give you 4000 samples of the universe. I mean, I guess 4000 is also not sufficient, but definitely better than 64. So these batch sizes are really important, because they tell you what is the universe. So now, if I decide to fine tune these models, what will be the hardware requirement? So one is, of course, the trainable weights. But when you have to train, you do backpropagation. There are some optimizer states that you have to keep. There will be gradients that you will have to keep. There will be forward activations that you have to keep, and some registers here and there. So typically, if you just add them all together, they typically will be 20x the size of the weights. So the model size in GPT-3 was 175 billion. You want to train it, you require 20 times the memory of that, roughly, to just load it into the memory. Not going to work. The other is the storage. Think from the AWS point of view or the Amazon point of view. So somebody is running, let's say the ChatGPT for the military document. I need to keep one LLM for the QA. Somebody wants summarization, I want another LLM for this. So this is 175 billion, 175 billion, 175 billion. I'm just keeping the copies. Okay, so not efficient or viable from the hardware requirement, not viable from the storage requirement. Okay, so what I'm going to do is, I will have 175 billion weights here of the LLM. I mean, I'm just saying use the word LLM here, but you can imagine any foundational model. So I'll use this 175 billion weights here, and I'll just put a wrapper on it. And this wrapper will be 10,000 weights, 1,000 parameters, something like this. So it's a very thin wrapper that I'm going to put for each of these tasks. And so this 175 billion will stay as it is, and this 10,000 wrapper will become different for everybody else. So from the Amazon point of view, I'll just keep this 175 billion loaded all the time, and whenever you'll ask, I'll load 10,000 more weights. And what I have to really tell you from here on is how to design this annular 10,000 weights thing. Okay? And now you can understand what will be the benefit if I manage to do it. Reduce computational cost, lower hardware requirement, better modeling. So because overfitting will also happen if you start training the 175 billion, less storage, all that stuff. So before I can tell you how to design that wrapper, I have to just ground what is a prompt here, because that's the word that I'm going to use now. So somewhere down the line, people discovered that if you train a large enough model on, so of course a large enough model will need to be trained on large enough data also. So if you train a large enough model on a large enough data, something interesting happens. The model somehow starts to learn everything. Everything in the sense that I just tell it what to do, and it does it. Okay, so I prompt the model, translate English to French, cheese, arrow. If I just say it, it gives me this output, the translation of English to French. I can give a single short example. So I can say the model, translate English to French, sea otter, and then lotter to more, which is the output of this. And then I ask cheese, and then it outputs the translation of the cheese. Now, I need to now justify my previous 1 hour. When I say that I prompt the model this, what happens in the transformer? I mean, if you have to really encode, where is this prompt going? I mean, it's a transformer model. And I said that I'm prompting this transformer. I mean, this transformer model is 175 billion parameter, it doesn't matter. It's a transformer. Where is this going? Okay, so remember I told you X. X1, X2, X3, X4, X5, X6, X7, X8, X9, X10. And X11 is what I'm predicting, just like the classification token. Okay, so I have trained the model for next word prediction. So I gave all the sentences, what I could lay on my hand on Wikipedia, Wikibooks, this, that. All I was saying is give X1 to X10, predict X11. Okay, by the way, this X10 is actually 4,000 long, typically, the context. But X1 to X4000, and then I predict X4001. That's what I was training the model for. And somehow, at the test time, when I give this length input, and I ask it to predict what will come in the classification token, or the next word prediction, the prediction comes out to be the translation of the French. Okay, so, and the word that we gave for it is that this is an emergent behavior. It's not that we planned for it. We just had enough model, pushed all kinds of data onto it. Somehow the model can learn through the instructions. I'm instructing the model in X's. I'm giving the instruction in the tokens. And the next word prediction automatically follows that. It need not happen, but it happens. Okay, and I can give more examples also. Now you can understand the impact of this statement. I mean, I'm just trying to tell you this statement, but we have to understand the impact of this statement also. This thing, English to French, initially if I had to update the model, so I gave you a particular model and I say, okay, you have learned the representation, now make it translation model. I required an AI engineer would have to give him some data which would have required some $10,000 and salary of the AI engineer, and then maybe $20,000, and I have the model which can translate English to French. I have made it 0 because this is any user can do. So remember, so I said that I'm bring down the requirement of expertise one notch lower. Or what I can say is, I mean, that's a negative statement that I'm requiring less. I'm saying that I'm increasing the skill of the person. So previously, I required an AI engineer to be able to do this. Now I require a simple computer program to do this. So I've increased the skill, improved the skill or the ability of that person. You can do more. So when I do this, this is called 0 shot. Okay, so 0 shot. Because I have not given you any example, I just said translate English to French, no example, and I just did. This is called a single shot because I have given you one example and the model has to mimic it. And this will be called few shot because I have given you few samples. But remember when I said you that I require few samples, it will typically mean 8, 10, 16, that kind of a number. Here I'm just saying 3. So take a model, give 3 examples and update the model to do your task. What people figured out is that if I give an example of this kind, so if it's a logical question, mathematical question kind of stuff, so I give you a question and I say that the answer is 11, then I ask my question. So this is the prompt and this is my actual query. But in terms of the transformer, this whole thing will go as x1s and xn's. And then what I'm really outputting is whatever the next token and next token and next token. And the answer is incorrect. I mean, so the next token that is being predicted is actually incorrect. That's what people figured out. Then what somebody else figured out is that if I give a detailed answer, okay? So if I give it, so I ask a question, so this is still a prompt. So the prompt was like this, now I give a detailed prompt. So I give a detailed, I mean, I of course give the same question, but I give a detailed answer. And then I ask my question. The model now mimics this style of answering. And the answer also becomes correct. And this thing in the NLP started to get known as the COT, which stands for chain of thought. So I not only tell the model the answer, I also give how to reason. And then the model is able to mimic that reasoning. But remember, it's not a magic wand, it's a next word prediction. So which means that I can give you the correct chain of thought in the prompt. The model gives a very incorrect reasoning, yet somehow gives correct answer. Okay, so don't try to see it as that the model somehow learns the reasoning in one example. It does not. It's just that it sort of starts mimicking this line of answering. And perhaps when you do this next word prediction, in this line of answering, the answer is a little more correct than the otherwise. Okay, so the chain of thought is a good fancy word, but it's not really training the model for the reasoning, it's just training the model how to do the next word prediction. So this is called prompt. But what you can see here is that this is a prompt which the user generated. Okay, and many times that's undesirable, not feasible, not viable, whatever you say. So what we want to do is do more than this. So whatever I have said to you now, I'll call hard prompt. It's like something the user gave, like a discrete vectors. See, because ultimately to the model, these are all vectors. So I gave certain vectors to my model as the x's, and then I asked the next word prediction. The question that I'm going to ask is, do I really need these hard discrete vectors, or I can do better than that? But the context remains the same, that I will give only few examples. Okay, and few as in 10, 16, that kind of a number. So now the first work that I'm going to describe in this style of technique is speed tuning, and I would have liked to call it prompt tuning, but prompt tuning is a word which has already been taken, in the sense that when you try to give different hard prompts to a model and see which gives the better answer, that's also called prompt tuning. So I'll just say p-tuning, okay, just to differentiate the two. But I may inadvertently maybe saying prompt tuning for this also. So now let's say you wanted an answer, what is the capital of Britain? Okay. Now what would you do in the regular GPT style? You will say, you will have this prompt generator, this may be a human being, will say the capital of Britain is, and mask, because that's the answer that I want. And I'll generate embedding for each of them and give it to the chat GPT, BERT, etc. It will generate something in place of this mask, and that's my answer. Okay, that's how it's going to work. Now, somebody will question soon enough that why the capital of, etc., etc. Because ultimately, to the GPT and BERT, these are all vectors. Okay, so x1, x2, x3, x4, x5, and then I'm predicting x6. Now, why should the vector corresponding to is the best vector? Why don't you optimize for it? Now, what will I do is, I say, okay, I won't say the. There are two words which are important, which I cannot change, which is that I want the capital of Britain. So these two words are fixed, have to be fixed, because that's what I want the answer. Rest everything is made up. So I can change the made up things. So I say, okay, capital and Britain, keep them fixed. H0 to HI, H0 to HI and HI plus 1 to HM, just keep some vector. Okay, so start with some random vectors. Give me some Q and A's. It's like capital of Britain is London, so I'll have the answer London. I'll backpropagate and update these H's. Now this H's will become something, and this H's something is something that I will use, and not the vector corresponding to the, and not the vector corresponding to of. Okay, now you can imagine how many samples I need really to train these vectors. And what we'll find out is typically 10, 16 will be enough. Now, the things are pretty obvious from here on. Now, you can argue that, oh, you started with a random vector and trained with 16 samples. So 16 samples and random vector became something good. Maybe the is the better vector. So I can always do mix and match. I can say, okay, let's initialize this H with the, but let's fine tune with the 16 samples. I can also say that have this 10 vectors here, 10 vectors here, and train it over the whole data set while you were training the transformer, but allow them to update during the fine tuning. So everything is possible. The core idea does not change, because what I'm saying is that I'm not using the discrete vector the and of, and I'm allowing the learned vector here. How you initialize, there can be n different ways of initializing, and of course one will work better than the other. Now what can also happen is that I say, okay, let's not change the and of also. So the capital of Britain, let's just keep them as it is, and just add 3 more vectors of yours. As I said, in the transformer, number of tokens does not matter. So I say, okay, 3 more vectors, and now you have output, backpropagate and train these 3 vectors. Now if you imagine that these are 512 dimension vector, so 512 into 3, so you require about 1500 parameters to train, and that's it. Because rest anything is not changing. But when I'm forward passing, this vector will attend to this vector, and this feature vector is dependent upon this also. So this whole pipeline has changed actually, but by changing very few parameters here. And now it becomes easy for an Amazon and Microsoft, because now what they will say is that I take an LLM. For a task, I have these samples and I learned what should be my prompt that I should add. I take another task, I learn what other prompts that I should run. See, this could be fixed, this could be vectors, and I get my output. At the test time, I get the same LLM. I don't have to change because it was frozen anyways. And depending upon what the task, I use different prompts. And my model is giving different answer. So I saved memory, I saved training time, everything, and my model is working as it is. And what people figured out is that it works quite good actually. So this is prompt design, this is like the hard-coded prompt, the capital of, and this is if you learn the vectors. Of course, if you can do the model tuning, it can work even better, but in many cases, that's not an option that you have. Okay? Now, again, things are pretty obvious from here. So now let's try to see prefix tuning. So what somebody will say is that, okay, so this is this vector. Now, if I'm taking this vector, what is happening here and what is happening here? So I'm just changing the vectors in the beginning. What if I try to change something in every layer? So what you can do is now, you will have the same vector, but now you will add another vector into these. So remember, this is going to become Q, K, and V. So now what I can take is, I can say that there is a K vector and I'm going to add something into it. Okay, and what I add is what is changing. So this is what the prefix tuning will become. So this is my regular transformer block. So I had multi-head self-attention, MLP. So MLP can be called fully connected layer also. Layer norm, MLP, layer norm. And I had some skip connections. Now what I'm going to do is, this input that is going to come, I'll take this soft prompt, I'll pass it through an MLP and just concatenate. But now this is in every block. It's not only in the first layer, it's in every layer. So that's what I will call the prefix tuning. Then somebody figured out that the prompt tuning or the prefix tuning is typically okay for easy tasks. But if the task becomes difficult, or if the model is not large enough, the prompt tuning has limited benefits. So what can I do more? Again, I do not want to change all the weights. So what I'll do is, I had this multi-head self-attention and fully connected layers. So I'll say, okay, let's keep all of them same. Just add one more layer here in between. And remember, this layer has to be small because I'm trying to train from very few data samples. So I can have this multi-head self-attention MLP, and then I have one more MLP sort of, which is getting trained through these 16 samples that I have. Okay, and so I'm just blown up here the adapter. So what you have is, here is one MLP, one layer. It's like a linear transformation, then you have nonlinear activation, then you have one more linear transformation. And the reason for doing this kind of a stuff is because, let's say this input to this adapter will be, let's say 4000 dimension. Now you have one 4000 and output has to be also 4000 because you can't change the input and output dimension. Okay, so one adapter is like 4000 dimension input, 4000 dimension output. Matrix size immediately becomes how much? 16 million. Okay, so you have 16 million weights immediately. So this is not going to work. So what you need to do is, you have to take this 4000 dimension and maybe project it to, let's say, 100 dimension. Now you have 4000 dimension, you project it to 100 dimension, and then you have a nonlinear activation, and then 100 to back to 4000. What will be the number of parameters? So 4000, 40,000 and 0.4 million. Okay, so 0.4 million here and 0.4 million here. So still 0.8. And I can just keep on lowering this dimension from 100 to let's say 10, and I may have even only 80,000 parameters. So adapter from 4,000 to 4,000 is not feasible in most of the circumstances. So what you have to have is some lower projection from 4,000 to some smaller number, and from that smaller number back to the original number. That's the only way the adapter can be designed. And then what people figured out is that the adapters work quite amazingly. So these are the number of trainable parameters. So remember now I have this control parameter in my hand, how much I'm low projecting. So if I'm projecting to a very low number, I will have a very less number of training parameters. If I'm projecting to larger number, I will have more trainable parameters. But what people figured out is that even with very small number of parameters, so I'm talking about 10 to the power 5 here in between, I can actually do a reasonable accuracy as I would have done with 10 to the power 8. So this small transformation that I can do actually helps a lot. Okay, but the flip side is that, so this is something that I already told you. It reduces the number of parameters, d-dimensional feature into some smaller m-dimensional stuff, and whatever I'm lower dimensional projecting actually determines how many parameters that, or what is the capacity of the adapter that I'm using. Okay, but using from large to small is essential. On the other hand, unlike the prompt tuning, where I could have used the same model and just changed the prompt, in the case of adapter, I'm sort of changing something in between. So it does not benefit the Amazons and Microsofts because they have to now load different model for everybody. But from our perspective, when we want to say that I want to train the model with a very small number of parameters, that still helps. Okay, so in that sense, the adapters are somewhere in between the prompt tuning and the full fine tuning. So the full fine tuning requires lots and lots of memory. The prompt tuning just does not require, or let's say require very least amount of memory. The adapter will come somewhere in between. Okay, now what you should notice here is that I added the adapter here, and I said that this adapter has to go to the the adapter has to go to the lower dimension, and then from lower dimension back to the upper dimension. Okay, I can actually represent it in the other manner, that let's imagine that this was a vector, and this one layer of the neural network is, I'm treating it as a matrix which is projecting it to a lower dimension. Okay, so it's like this is 1000 dimension, this is 2 dimensions, so it's like a 1000 cross 2 matrix that I have. Or in other words, in general the transformation matrix would have a rank of 1000, but the rank that I am choosing is a low rank one, which is 2 in this case. So what we are saying is that in the transformations, converting or using the matrix which is of the low rank actually helps in reducing the number of parameters without necessarily decreasing the accuracy of the model. So I'll skip this. Okay, and this fact which was there in the adapter, that I can actually make the metric, the transformation metric low rank, I can now formalize it using this kind of visualization. So for example, I typically have, let's say, this embedding this input x, and I pass it through a matrix W. So for example, x to q. So this is a matrix W which converts that into an embedding which is of h, which could be q or k or v. Now when I do full fine tuning, I take this vectors W, I find the gradient and find out what should be the delta W weight update into it. And then whatever the delta W comes out to be, I add this W plus delta and make it W prime. And that's how I will do the next inference, I'll compute the next gradient and keep on doing it. What one can look at is, because I'm saying that I am just computing a change to the gradient, so there are some pre-trained W. I computed some delta W, this should have been delta W. I computed some delta W here. These are my updated. And then what I'm saying is that this is, I'm saying x times W plus delta. Now I'm saying x times W and x times delta W. And I'm adding in them later on. So that's all I am doing. Now, this is useful because once I look at it in this manner, that there is a W and there is a delta W, people figured out that although this W can be large, so this W can be a 4000 by 4000 matrix, which I have learned with large amount of data, but this delta W, which is of the same size, is like 4000 by 4000, need not be of the rank 4000. Even if I choose the rank which is much smaller, this delta W is still okay. The argument is actually the other way around. The delta W that we update, the rank of it comes out to be actually very smaller. And then there was some analysis which was done which says that, okay, if I do the full fine tuning, and if I say that, let's say the accuracy comes out to be A, what is the minimum rank of this delta W that I can choose so that the accuracy is not below 0.9 of A? Okay, so full fine tuning will lead me to the 100% accuracy. I don't want to go below 90%. What is the rank that I can choose? Okay, and this quantity, this rank, was called the intrinsic dimension of the task. So if I'm choosing for the, let's say I have pre-trained the model, I'm updating the model for the summarization, and I'm doing full fine tuning. So I did full fine tuning, the accuracy comes out to be A. Now I say that the weight update will not be a 4000 rank matrix, it will be only 100 rank matrix. What will be the accuracy be? And I say, oh, it's already still 95%, even if I choose rank 10. I say, okay, let's decrease it further, rank 5. At some point, the accuracy will go below 0.9. Okay, so whatever that rank is called the intrinsic dimension of intrinsic dimension. And what people figured out in this work that I'm citing here, that this rank is often very, very small. So I can take a model pre-trained on a large amount of data and update for the summarization, and this update that requires is rank 10, rank 5 metrics typically. So this was utilized in this work, which is called a low rank adaptation. It's also an adapter, by the way, but it's an adapter which explicitly says that I'll take this W and I'll take this delta W, and I'll assume that this delta W is low rank. Okay, and low rank as in very low rank. So this could be a 4000 rank and this could be rank 5 or rank 4. That's low rank. And it does not change because all I'm saying is that I was making this embedding which was x times W0, this was the original weights, and I'm learning this delta W, and this delta W is something that I'm modeling as B times A. And this B and A are low rank matrices. That's how this delta W will become the low rank matrix. So there is this X gets multiplied by the WA, low rank matrix, then up by the WB. Now what you should notice is the eventual implementation that I'm doing is not very different than what I was saying in the adapter. That I'll have this adapter which will take some 100 dimension, will downsample it to 10, then from 10 to 100. It's required because otherwise the number of parameters will blow up. Now in the low rank adaptation becomes a little more principled fashion. Not a lot is changing. Now I'm saying that I'm explicitly keeping it as a low rank matrix. It's not that it will happen automatically, I'm just keeping it as that. And so once I look at it into the low rank way, I can actually adapt in various styles. So first of all, what we have to understand is that just like in the case of adapter, now this rank becomes an hyperparameter. So if I choose small rank, my accuracy may not go very high, but my number of parameters will be very few. If I choose a large rank, my number of parameters that I need to train will become large, and the accuracy can also become large. So there is a trade-off that will happen here. But now this low rank style of adaptation will give me a hyperparameter in my hand, or is the way in my hand how to really choose this A and B. So what will happen is that in the low rank adaptation, which is the LoRa work that I'm mentioning, the B matrix will be initialized to 0. And the A matrix will be initialized to Gaussian with 0 mean and a variance sigma. Now why is that important? Because understand that when I'm doing the initialization, this multiplication will ensure that the output, the contribution of this branch is almost 0. So unlike the previous cases, if I had actually initialized them randomly, then it could have disturbed these features. So it's like that I have, let's say X is becoming 100, and then I suddenly add plus 10 or plus 20 into it because it's a random initialization. So it disturbs the whole output. So what we say is that initially you should add only very small amount, maybe 100.01. Don't change a lot, because this 0 will ensure that actually nothing is going in as an addition. Slowly, from the back propagation, this will start to change from 0 to something. So 100 to 100.1, 100.2. So I'm just changing a lot slowly. And even when I'm changing this number, this n0 sigmas will ensure that these weight changes are uniform. They're not biased in one particular way or other. So when I say 100.1, I also sometimes make 99.9. So I make the changes both ways. So the LoRa style of visualization of the adapter will actually help me put many principal things in place, how to really make that happen. And what will matter is that in practice, the LoRa may work better than the adapter, although on a larger level, they are not too different from each other. And that's why there are many people who are working with LoRa style of working. So we have the QLoRa, which is sort of quantized model. We have LoRa Plus, which is talking about different learning rates for A and B. We have dynamic LoRa, different runs, different ranks for different runs. So we have many more variants. The main process remains the same, that there is A and B for the delta W, and then you update them. So I'll just summarize all of them together. So this is what we discussed. So I have this transformer block, okay, X and Y. Now I can add an adapter, kind of a LoRa here. So this is LoRa. I could have done the prefix tuning where I add something into the K vectors or the V vectors. So this is my prefix tuning. I can have a regular adapter also here, which is like this, and I can update my transformer block. Okay, and of course there is another live not tune things which I said P tuning, where I just add the vectors into the beginning, and all of them are possible. I'll just quickly mention. I have 5 minutes, right? So I have somebody there. Yeah, so I'll try to finish in 5 minutes. So this is the clip which Vinod was showing you earlier. So I have this image encoder. So this is image 1, image 2. This is like my batch. I have corresponding text, an image of cat, an image of dog, etc. And then you try to align this image with this text. Okay, and then you update the text encoder and image encoder in such a fashion that you align. Now, this is a very generic word that I used here, that you align. Now, how do you align? And the details are how you align is either you use prompt tuning, or you will use adapter, you will use LoRa, you will use prefix tuning, you will something. Because this will be a 170 billion model, this will be another 170 billion model. So you have been given a model for, let's say, natural image classification. You want to do it for the medical image classification. You take Roberta here, you take VIT, something here. How do you train? How do you update for your medical image classification? You say, okay, I have few samples, 500 samples, 100 samples. So I have the same stuff, I'll add an encoder here. And I'll train this adapter in the image encoder, and that's the new image encoder that I'll have, and which is the one that I will use. I can also say that ultimately this image will go as tokens. Okay, so remember when I showed you the VIT, I said that I'll take the patches and put them into words. So these were tokens. I can add few more tokens here. That's prompt tuning. I could also say that the image of a dog is not a good word. I'll have few more vectors in there. That's P tuning in the text. I could also say that I'll do some mix and match of these things. And everything is feasible. So this is clip 0 shot. That I take this training and I'm doing this inference where I say that, okay, I'll take an image of a penguin, an image of a panda, an image of something, some text encoding will come, and I'll do this dot product. Whichever comes out, that's my classification. But most of the time, it's not going to work if you just change the context, let's say medical image classification. Now you have to update these encoders in some manner. Now how do you update? You'll say, okay, I don't have the bandwidth or the compute or anything, resources to really do that. What I'll do is, an image of a penguin, I'll just add one more vector. P-tuning. I'll say, I'll take this token, add few more vector. Visual prompt tuning. I'll say that, okay, in the text encoder, wherever the K, I'll just add something into that vector. Prefix tuning. I'll say this image encoder is ultimately 92 layers. Between the two layers, I'll just add one adapter. I'll say, okay, I'll make them low rank, LoRa. So you have a task, you have a certain sample, and you have to update these guys somehow. And that's where whatever we did will become relevant. And there are names for it. So for example, when you take this text and then you add learnable vectors into it, and then you sort of update the clip. This is the paper which was co-op, came in 2022, where we said that, okay, let's do context optimization. Okay, then somebody figured out that this is pre-trained on a data set, not a good idea. Let me just add a vector into it through the image. Okay, so now I have this vector, which I sort of learned over the data set. At the test time, I get an image, I pass it in encoder, I learn this one more meta net. It gives me a vector and I just add this vector into all these prompts. Somebody figured out why to keep text and image separate. Let's put them together. So this is classical co-op or co-op later. So you say, okay, let's do cross between image and text. So the PEFT things that I mentioned will remain broadly the same. So these are so many ideas that you can use, but you will use them in quite a mix and match ways for different applications. And this is the last thing that I wanted to show, the visual prompt tuning, where I have this classification and I just add few more vectors in there. And just like I showed you for the prefix tuning and p-tuning, I can add the shallow tuning where I just add in the first layer, or I can train it in all the layers which they call the deep tuning. So you have big model and you are sort of keeping most of the model frozen and just training some small part of it with very few amount of data is what we will call the PEFT. Yeah, I'll end my lecture here. Questions?
Good afternoon, sir. I'm Zaman Shrestha. So, I kind of got confused on the 3D kernel part. So how does that work? We can visualize the 2D kernels, right? We can manually do the convolution in 2D. So how does that work in 3D?
So, I think that was the purpose of asking that question. That in the 2D one can visualize, so you can use your intuition and maybe guesswork to really do that. Once you have to 3D, you really need to know how the computation will happen because you can't imagine things. So because now it has become 4D. So the right way of looking at the convolution is that one is how the convolution kernel is moving, that is determining the size of the, or the dimension of the convolution, 2D or 3D or 4D. And the other is on what data this kernel is operating, that's the size of the input vector. So in the case of the image, it's a pixel that I have. And the weighted sum is over the pixel. This pixel could be of 3 dimension, could be of 300 dimension. But the convolution will remain 2D because it's on the image and the window is moving in 2D over the image. Although when I was computing the weight size was 3 cross 3 cross 3 because 3 cross 3 is actually the convolution kernel size. But the weighted sum between the input and the weight has to be in the same dimensional vectors. So if I take A dot B, A and B have to be of the same dimension. So when in the same manner, when I say convolutional weights, in the case of 2D, the convolutional kernel is 2D, correct? But each weight is not a single scalar anymore, it's a vector. And this vector has to be of the same dimension as the input, which in this case is an RGB, which is a 3D. So it's a 2D convolution where each weight vector is of 3D. In the case of hyperspectral images, it's a 2D convolutional kernel where each weight vector became underdimensional. But it's a 2D convolution. Okay? See, normally when we show you the convolution kernel, we show you 3 by 3 window and we write some scalars. But that's true only when it's a grayscale image. When it's an RGB image, this weighted sum has to be done with the R, G and B 3 channels. So I cannot have one scalar there. I need to have 3 scalars because one will get multiplied with R, the other will get multiplied with G, the other will get multiplied with B. So I need to have 3 numbers. So each weight is not a scalar anymore, it's a 3-dimensional vector. In the case of hyperspectral image, it's a 100-dimensional vector. But it's a 2D because I'm plotting it as 2D. It's a 2D, the window will move in a 2D plane. So there's a dimension of the convolution and there's a dimension of the vector on which it operates. And these are two different things. In the case of 3D convolution, the operation is over a voxel. So it's like X, Y, and Z. Or when I say the video, X, Y, and T. So the operation is over a voxel. I'm doing weighted sum over a voxel. I'm doing a weighted sum over a cube or cuboid. So just like it was a square or a rectangle in 2D, in the 3D it became a cuboid. So I had 3 cross 3 cross 3 because the cuboid requires 3 dimensions to explain. So now the convolution is a volume and this small cuboid sort of moves over this volume for the convolution. But again, just like the previous case, each of this multiplication need to be of the same vector sizes. So if I take an RGB image, it will be 3. If I take an hyperspectral video, it will become 3 cross 3 cross 3, that's the size of the cuboid, times the vector size, which in the case of the hyperspectral will be 100. So just treat these two things separately. One is what is the dimension of a convolution, and the other what is the vector on which it is operating.
So can you say that the final dimension that we added, it's just representing the time?
Okay, so that's
It's moving on the time.
So that's the other question that I should have asked. But I'll just let the other people ask any question if they have, then I'll answer that first, and otherwise I'll come back. I'll use the time to answer your question.
Thanks a lot for the presentation. So we have a use case where you have a data set of images, and you're trying to compare the accuracy between convolution neural networks and vision transformers. If the size of the data set is small, it's hard, you have a high chance that the convolution neural network will outperform vision transformer. But if the size of the data set is very big or large, the vision transformer outperforms convolution neural network. Why?
So I have two comments to offer here. So one, I can answer what your question is, and then I can also explain that I can actually flip your observation also. That the VIT will work better than the CNN even in the small data. But anyway, so I'll just first answer your question. So if you have not done anything else, then there are stronger constraints that I have put in the CNN. I have said that the weights will be local, 3 cross 3, and it will be translation variant. So there are stronger constraints that I have put on my learning problem. And just like in the case of, let's say, linear versus quadratic, I have used sort of a linear model. So with a small amount of data, it's likely to not cause the overfitting and the things will work as fine. But if I start using the quadratic model, the chances are that it will overfit on the small data. So in the same manner, the convolution is a slightly more constrained model, which means that it's likely to work better in the smaller data set. So that's the answer to your question. But now bringing it back to the context of the foundational model, the game has changed actually. I'm asking you that in the clip, I actually fine-tuned with 100 samples and it will work better than the CNN. And why that is going to happen is because there is one more factor which has got into the scheme, which is what is the pre-training on. So one is of course your data, the supervised learning that will happen, but on what data size or what type the pre-training has happened is also a determining factor now in how the model will eventually perform. So let's not look at the size only of the supervised fine-tuning that I'm doing, but also the pre-training. And the chances are that even if my transfer model has less constrained model, because I have been able to use large amount of data, I have still been able to train it perfectly fine. And they will adapt very quickly to the small data set. So this observation can also flip.
All right, thanks.
So if we have time, then I can answer this question. Do we have time? Yeah, okay. So I can answer your question. So, but in that case, I'll have to first ask my question first so that I can get that answer. So now let's put the reverse. So I have a 2 to 4 by 2 to 4 by 16 volume of the video, or the clip, whatever you want to say. I run a 3 cross 3 cross 3 convolution on top of it. What is the output size? I mean, just think about it. See, because, I mean, now you cannot imagine. You have to just understand the concepts, and that's the only way to answer. It's a 4D space, you will not be able to imagine. I'll just say that again. 2 to 4 by 2 to 4 by 3 volume. I mean, 2 to 4 by 2 to 4 by, yeah, sorry. 2 to 4 by 2 to 4 by 16 is the volume. Each frame is RGB. Okay? What will be the output size if I run a 3 cross 3 cross 3 convolution on this volume? So then I can answer your question. I mean, you can do it in stages. Let's say assume first there is only one kernel and then answer, and then try to see if it becomes 54, what would be that. So clearly, first of all, the input tensor, if I say, is 2 to 4 by 2 to 4 by 16 by 3. There is a 4-dimensional tensor also because it's an RGB frame. The output dimension of the tensor will be what? Okay, so now let's just take a step back and think how would you have done it for the 2D. So if it were a 2 to 4 by 2 to 4 image, and I would have done 3 cross 3 convolution, you would have said size to be what? So typically we subtract the kernel size from the image. Okay, because of this boundary it's stuck, so the kernel cannot go out. So something will get subtracted from the left, something will get subtracted from the right. Overall, the kernel size will get subtracted. Or if I put the zero padding, I can say the output will remain the same because I'll just add some zeros on the border. So either I can say 2 to 1 by 2 to 1, or if I am willing to do the zero padding, I'll say 2 to 4 by 2 to 4. That's also the output size. Okay, so the kernel size does not really change the output. Now, if I were in the 2D again, I would have given you the image 2 to 4 by 2 to 4 by 3 tensor, and the output size was 2 to 4 by 2 to 4. Because I was learning 54 kernels, I got 2 to 4 by 2 to 4 by 54 tensor. That was in 2D. Let's try to see it how will that happen in 3D now. So now I have 2 to 4 by 2 to 4 by 16 tensor as the input. Remember, I am keeping convolution and the size of the vector as two different things. So this convolution is happening in 3D, which is 2 to 4 by 2 to 4 by 16. Each element is a vector of size 3 that's incidental to the problem. That does not change anything in my output. So my output tensor will be 2 to 4 by 2 to 4 by 16 if I'm willing to do the zero padding. If I'm not willing to do the zero padding, just subtract 3 from every one. 2 to 1 by 2 to 1 by 13. Why? Because even if the element is of dimension 3 in the RGB, my weight vector is also of size 3. I do a dot product, I still get a scalar. So weight vector could be of whatever dimension it wants to be. My output will remain a scalar. So even if I had hyperspectral image here, where this RGB 3 channel would have become 100 channel, the weight vector would have also scaled by that number. The dot product would still have been a single scalar. So the tensors will remain 2 to 4 by 2 to 4 by 16, whether I talk about RGB or the hyperspectral. And because I am learning 54 such kernels, so the tensor will become 2 to 4 by 2 to 4 by 16 by 54. So the RGB has no consequence on the output tensor, because it's going to get dot product with the vector and will give me a scalar. It has the consequences on the number of parameters. It has no consequence on the size of the output tensor. Similarly, when I'm computing the number of parameters, the size of the input tensor has no consequence. The number of channels do have the consequence. So it's different for different things. Okay?
Thank you, sir.
We have in Nepal. So this is a
The
like a
Vajra.
wood. No, it's not a Vajra. It's something that holds this structure together. So this just signifies your contribution. Thank you so much for coming.
Hi, I'm Chetan. I'm a faculty in Computer Science department at IIT Delhi. This was my first trip to Nepal, and thanks to the organizer for inviting me. And it was wonderful experience, both in Kathmandu initially and now today at the lecture. I'm really amazed at the level of enthusiasm, the energy, I mean, that I saw today, and even yesterday there was an event on the panel discussion, etc., for the entrepreneurs. And I think kudos to you guys, wonderfully managed, very nice, and all the best to everyone here. Thank you.